We have here two large bioretentions which I've known for years. Both of them are around 600 something square meters, and if you can notice, both of them look pretty lush. This is the overflow from the bioretention, and this is how the bioretention looks like. You can notice is a pretty lush bioretention, good coverage. There's some trees there. Now, it's not necessarily poorly maintained or anything. It's just very lush. We're going back here. This is the other bioretention. You can see now all the bioretention plants. They all live very well. There's a bit of GPT here, so on and so forth. So why are we showing you, or why am I showing you these bioretentions? For a very good reason. Many councils and many authorities, such as our good friends at Melbourne Water, suggest that we should use these here bioretentions for cooling, for dual purpose, cooling of the climate. Well, let's see how cooling goes. You notice wherever there's a tree, the temperature is very cool. Where there's no tree in actual bioretention area, it's not that cool. It gets pretty red, and obviously where there's a soil, it's very hot. Now, on the day I took the screenshots in the video, which is today, 22.4 degrees was the temperature. Highest was 23. Luckily for us, I took some screenshots of how hot things are. Bioretention here, good coverage, good plants. They live pretty well. It's been a lot of rain lately, so everything is relatively good. Overflow from the bioretentions. What is happening? Still pretty red. Wherever there's trees, pretty dark. The bigger the trees, the darker the color. What does that mean? Temperature where there's no coverage, 43 degrees. 23 here, 43 here. Let's see, 28 degrees where there's a bio, 20 degrees where there's a tree. 22 degrees where there's a bit of a tree, 30 degrees only where the bio is. This is a different location. I know this location well. This is a bio that doesn't do as well as the previous one. So the previous one is the most successful, by the looks of it, the most successful bio you can potentially have. So this is a bio that is not as successful as the previous one. You can notice the tree here. Boom, hot, quite cool. 43 degrees around the bio, and again, everything so red here around the bio, and see how cool where the trees are. 48 degrees here, 40 degrees here, and unfortunately I don't have a screenshot, a temperature reading here, but it's somewhere very like around the 22, 23, 24 degrees. 40 degrees in the bio, sometimes 48. Around here it will be around high 30s, low 30s, or not even mid 30s in here, 20s in here. In the same location, 23 degrees here where there's a tree, 29 here degrees where this is not a bio but it's a cover. You can see here, this is actually supposed to be a wetland, but you can see where the wetland is covered by plants. The temperature gets quite high. All these plants are here in the wetland. There's a pipe coming and feeding a wetland in here. Here's a little bit of water surface and the wetland here. And this is another shot of the wetland here with the area that was pretty hot. And this is a small tree. It's not a huge tree or anything, and it still like temperature drops significantly compared to everywhere else around. So why is this relevant? It's relevant because many times authorities suggest to us use a bioretention instead of a filter and a gross pollutant trap because it achieves the dual purpose of cooling in addition to treating the water. So it's like dual purpose infrastructure. As usual, when we make assumptions without really testing the assumptions, we end up being extremely wrong. And by we, I mean Melbourne Water and people like them. You cannot reasonably expect the bioretention to provide cooling when we can see on an infrared in a very cool day, 23 degrees out there, and sunny, not very terrible. I've done this test previously in hotter days, and it's actually significantly worse. We can see that the trees behave far better in terms of cooling than a bioretention. The bioretention occasionally has very, very little impact compared to just simply asphalt or dirt. So what we should do, we should make sure that when we specify stormwater quality, we put a filter or something that's as efficient as possible. You can put it underground and you can offset that with a tree or two. This will achieve far better results than putting a bioretention in the worst possible hydraulic space, maybe impeding your flow path or creating erosion problems, so on and so forth, losing land in a very specific spot that may not be useful for the developer. What we should do is we should achieve the treatment in the most beneficial way for stormwater quality and forget about the secondary benefit of cooling, because that's pretty much useless. In my opinion, what we can do is we can say, look, I'm gonna offset what you would hope to be a bioretention with a tree, because trees are far more effective in terms of shading and cooling. And that's it. You can say, okay, for every 500 square meters of land, I'll give you a tree. I'll put the tree wherever is convenient for the developer, and this way council, but generally the authority should be satisfied that actually the benefits of the environmental benefits are achieved without creating significant trouble for the developer and for the designer when they're trying to achieve stormwater quality. Thank you.